There is a large storage tank full of water that has a radius of 8 meters. A small hole with a radius of 0.02 meters is drilled in the bottom and water flows out at 35 meters per second. Assume that the pressure at location 1 is the same as at location 2, and that's what we're going to call atmospheric pressure. What is the velocity of the water dropping in the large section of the tank? So we have a big water tank. And this tank has a radius of 8 meters. Put that in perspective, it's about 25 feet in radius, which means it's about 50 feet in diameter. That's a big tank, right? That's big. Okay, so we have a radius of 8 meters. And someone chooses to drill a hole. Now, whether that hole is drilled like right there or right there, it really doesn't matter. But let's just say we drill a hole right here. Okay, so someone drills a hole, and now what happens is water comes out of that hole. But that hole is small and is 0.02 meters. Now, actually, that's a pretty big hole. It's almost two. That's a pretty good size hole. Like talking about a drill wise. Like if I'm going to drill a hole, that's like 20 centimeters in diameter, so that's a pretty big hole. But what's true about this, the size of the hole at the bottom compared to the overall size of the tank? What's true about my R1 versus my R2? They're kind of close or really, really different? They're different, and R1 is really, really, really big compared to R2. But what's going to happen is we're going to have water coming out of this tank, and because of the amount of water above it, it's going to come out at some speed, and according to the problem, it's coming out at 35 meters per second, which is really fast too for the record. But there's a lot of pressure from that water pushing down on it. So if we have an R1 of 8 and an R2 of 0.02 meters, water's coming out at 35 meters per second. The question being asked is, what's going to happen to this water level? If I drill a hole in the bottom of this tank, is this water going to stay here, or is it going to flow downwards? Or is it going to flow upwards? It's going to flow to the left. It's going to go down, right? This tank will drain downwards. And we could go through and we could call that a V1. And we can actually measure how fast that water drops in this tank. And we can call that velocity. Now, this isn't Bernoulli's yet, but it sets us up to a certain type of Bernoulli's problem that we're going to be using, in this section. So we have an R1, we have a V1, we have an R2, we have a V2. Now, if we have an R1 and an R2, boy, that sure seems like we could calculate some areas. We talk about a holding tank and a hole drilled in the bottom. And if we have a V2, that seems like it's setting us up for an A1 times V1 is equal to A2 times V2 type of problem. And it is. So we'll talk about a holding tank being a circular thing. A1 is equal to pi times R1 squared. And we can say A2 is pi times R2 squared. So plug in our numbers for R1, 8 squared, which again is like 25 feet, so big thing. A2 is 0.02 squared. When we plug these in, I'm going to try to keep every digit that I can in my calculator. And we get an A1 that's equal to 201.06 and a whole bunch of digits, which I'm going to keep in my calculator, meters squared. So 201 meters squared. So remember that box that was 1 meter by 1 meter? It's 201 of those. Big. It's big. And then if we take pi times our new radius, or R2 of 0.02 squared, we get an A2 that's equal to 0.001256, so we'll just say 0.0013 meters squared. Now we can do a flow rate. A1 times V1, unknown, is equal to A2 times V2. So A1, 201.06 times V1, that's what we're asked to solve for, how fast is this water dropping in the tank, which is equal to A2, which is 0.0013 times 35 meters per second. So if we multiply 0.0013, but really all the decimals in my calculator, times 35, we get 0.4398, blah, 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 blah. And then we divide by our A1 of 201.06192982. We get a V1 of 0.00022 meters per second. So let's talk quick about what that number means. If I drill a hole in the bottom of a tank, water's going to come running out. Will that tank empty out? Will it run out of water? Yes, right? It will run out of water. And that water level will drop with time. It's going to slowly go down, or it's going to go down, and eventually it's going to be at zero. Or it's going to be at the bottom, I should say. What this is saying is this water level is dropping at 0.0022 meters every second. Now, to do a quick kind of conversion, if we move the decimal point 2 times, that would be centimeters per second. If I move the decimal point 3 times, that's millimeters per second. So what this is saying is if I do that conversion, that tank, or my V1, is dropping at 0.22 millimeters every second. Is a millimeter big or small? Small, right? It's really small. It's dropping 0.2 of those every second. Or we do some kind of estimated math. It'll take about 4-ish seconds to drop 1 millimeter. So if I'm staring at a tank that's 8 meters in diameter, or I'm sorry, 8 meters as a radius, and I'm watching that far side of the water level, am I going to noticeably see that tank just going like downward? No. Will it empty? The answer is yes, it is going to empty. But it's going to drop at a very small level just because it's so big. So the idea that this draws us to is if R1 is greater than R2. I don't know if mathematically that's really a thing, but the point is if R1 is much greater than R2, if R1 is way, way, way bigger than R2, which I'd say R1 is way, way, way bigger, 8 meters versus 0.02 meters. So how much bigger does it have to be way, way, way bigger? I don't know. A lot. But if R1 is a lot bigger than R2, then we can make this kind of assumption that V1 is essentially 0 meters per second. It's an estimate, it's not obvious, it's not 100% accurate, because it really does drop. It is dropping at 0.22 millimeters every second, but that's essentially 0. It will move, yes, that tank will empty over time, but we can kind of use that as an assumption for when we do then deal with these, and we deal with the full Bernoulli's part of it. So when we talk about like a large tank or a large container that has a really, really, really small hole on it, then we can use this assumption, and we can talk about like V1 or V2, depending on what location you call it. The one that has a really big area, that velocity is essentially 0 when we drop it. So at the very top of that worksheet, there is Bernoulli's equation. And today we're going to start doing some calculations with Bernoulli's. And Bernoulli says P1 plus 1/2 rho V1 squared plus rho GH1 is equal to P2 plus 1/2 rho times V2 squared plus rho GH2. Okay, that's Bernoulli's equation. It's written on the top of your sheet. Right below it, I have 5 different variables, because there's really 5 different variables in here, and you need to know what they are. So what I'm asking you to do, I'm going to ask you to do it right now, is what does P represent? Okay, and then the second arrow would be what units do we measure P in? Then what does rho represent? And what does the units that we use for rho? That's what I'm going to ask you to do quick. Go through, there's 5 different variables. Define what these 5 variables mean. What does the P1, what does the P for P1 and P2 mean? I'll get you started. P stands for pressure. Okay, so on your sheet, what I'm asking you to do is where this says P, I want you to write pressure. And what units do we use to measure pressure? Kilopascals is how they did in chemistry. We just use pascals. Okay, we just use pascals. Did you say kilopascals? No. Okay. Yeah, so when they talk about atmospheric pressure, we often use kilopascals just because it's such a small number. But for all of our other units to work out, we use a Pascal. So it's just PA. Okay? So follow that trend and try the next 4. What does the rho stand for? What does the V stand for? What does the G stand for? And what does H stand for? And we can make some corrections. Maybe hold off on the units for right now and maybe just identify what they stand for. All right, what does rho stand for? What's that variable represent? So big P stood for pressure. What does the Greek letter rho represent? Density, yeah. So that's density. Anybody remember the units we use for density? It's kilograms per, and a big box in the back. Cubic meters, yeah. So how many kilograms per cubic meter is there? Now that's rho. This is also rho, so just for the same thing. What does V represent? Same thing it has all year. Good. And we measure that in meters per second. Okay, so V represents velocity. There we go. Rho, we already talked about rho, that's Greek letter for density. G stands for gravitational acceleration, units, meters per second squared. And what is that value here on Earth? 9.8 meters per second squared. Last is H. What do you think H represents?
Height.
Height, yep. So we're going to talk about what is the height of often a pipe, and we are going to measure that in meters. So that's what those variables represent. P1, P2 both stand for pressure. V1, V2 stand for velocity. Row, row, row your boat gently. The four rows that are listed, 2 on the left, 2 on the right, those represent density of the fluid. Now we aren't going to generally be switching fluids from location 1 to location 2, and the density of those won't change. That's why I don't have 1s and 2. It's not like row 1 and row 2. It's just row. What is the density of the fluid? We're not changing locations, so I'm not going to talk about gravitational acceleration at location 1 versus location 2, because we say it's relatively constant on the surface of the Earth. And then the last is going to be the height and how tall or how high up is that water. And when we talk about H, we often define the lowest point to be 0 and we measure from there. So we just got to figure out what value is 0 versus non-zero. Of these 5 variables, P1 and P2 are things we look for. We're comparing pressure at location 1, comparing it to pressure at location 2. We talk about velocity at location 1, and we compare it to the velocity at location 2. We talk about the height at location 1, and we compare it to the height at location 2. Those are really the 3 variables that we're comparing. G is 9.8. The density of the fluid, probably going to be water, probably going to be 1,000 kilograms per cubic meter, unless I tell you otherwise. So when we start using Bernoulli's equation, we're really looking for P1s and P2s, we're looking for V1s and V2s, we're looking for H1s and H2s. Those are the 3 variables that we tend to change. Now, I said it multiple times on Friday, hopefully someone can remember it for me. Bernoulli's principle says that the blank of fluid flows, the blank of pressure. So the faster, I already gave you the first, that the faster a fluid moves, what happens with pressure? So higher pressure, lower pressure, same pressure. Bernoulli says the faster a fluid moves, the lower the pressure, Okay? So Bernoulli's principle is essentially the faster a fluid moves, the lower that pressure is going to be. The faster that fluid flows, the lower the pressure. So the fastest moving air has the lowest pressure overall. Now, when we talk about speeds of fluids, we often talk about fluids moving through pipes. When we talk about changing the area of a pipe, does not affect the flow rate of the pipe. So if a pipe this big and it has 2 gallons per minute flowing through it, and I reduce that area, it still has 2 gallons per minute flowing through it. Well, what's going to be true about the speed of that fluid in a smaller pipe compared to the bigger pipe? Thumb over the end of the hose kind of thing. What happens to the speed if I put my thumb over the end of the hose? It increases, it goes faster, right? If I change my area, my velocity changes. So the thing that we have to do before we do a Bernoulli's calculation using that really long equation is we look at area and velocity. And I put it underneath that Bernoulli's, the faster the fluid moves, the lower the pressure. Now, the opposite is true of that is true as well, right? So instead of saying the faster the fluid moves, the lower the pressure, we could say the slower the fluid moves, the higher the pressure. The opposite. But if the area changes, then the velocity changes, and we have to do a flow rate problem first. We have to do an A1V1 equals A2V2, kind of like what we did on the board. We'd have to do a problem like that first before we could use this really long equation. But essentially, Bernoulli says the faster a fluid moves, the lower the pressure. So let's try to show you that with another amazing demonstration. Hopefully this kind of shows up. That is not going to show up. Hi, Mom. My mom watches my YouTube channel. She never has, actually. Well, actually, I don't know that. Maybe she's one of my 3 subscribers. Actually, I think I have 5.
You have like 20.
Huh?
You have like 20.
Do I really?
Yeah.
I have like 20 subscribers. Yes! All right. How many do I got to get before I make millions?
Like a million?
Oh. Okay. Well, I got a ways to go there. One of these days. All right. So I'll move this. I'll rotate this in just a moment so everyone can see this. But what I have is I have some. Actually, you guys are here. You get the first viewing of this. Not all my subscribers. They get second chance. Sure. Okay. So what I have is this glass pipe. It's called the Venturi tube, I believe is what it's called. But I have an air line. This is not natural gas that I'm hooked up to. This is gas. This is air, just for the record. I'm not running natural gas through here. You would smell it otherwise. But I have compressed air that can flow through this pipe, this hose, and it goes into this glass. And then what happens is my glass tube gets bigger, then it gets smaller, then it gets bigger, and then it gets smaller, and then it exits. And in the bottom I have some water. That's at the same level. So the idea is by blowing the air, the air is going to go all the way across and it's going to come out over here. What happens to the speed of my air when I go from a small area to a bigger area? Go slower, right? And then what happens to my speed as I go from a bigger area to a smaller area? Faster. And then what happens when I go from a small area to a bigger area? Slower. And then so on, right? So we get these differences in speeds. So as we go from here to here, this is going to be slower, where this is going to be faster. Let's just ignore location 3 for right now. We'll talk location 1, location 2. So between location 1 and location 2, where is my fluid air going to be moving the fastest? At location 1 or location 2? 2. And Bernoulli's principle says the fastest, right here, the faster a fluid moves, the blank the pressure, lower the pressure. So that means right here my pressure should be lower than right here, right? So what's going to happen to this water level? It's going to go up and down. Okay, I'm going to tell you that. It's going to go up and down. So my pressure here is fastest moving, so lower pressure, and this is going to be higher pressure over here. Is my fluid going to go like this, or is it going to go like this? Remember, higher pressure versus lower pressure. So higher is going to push it down or pull it up. Okay, good. Push it. So we'll try to turn this on slowly. Okay, so there we go. So we have fastest, which is lowest, versus slowest, which is highest, and these went like this, because this is higher pressure than lower pressure, so we get this different height. Okay. Okay, good. So, we get this difference in height. Now, I don't know the answer to this, unfortunately. So, this is highest, this is lowest pressure. I'm good with that. The thing I'm not 100% certain on is when this goes from here to here, I get it, but when this goes from here to here, this gets slower again. So why is this higher than this? I don't know. I don't know the answer to that, by the way. Because if anything, between this one, and this one, I get it that this is the fastest, so this should be the lowest pressure, so it should be the highest. But based upon the column height, then this is kind of implying that this is the second fastest, and then this would be the slowest or the third fastest. But you would think because of friction that this one would actually be moving slower than this one. I guess I'm not sure. But the idea is that this is kind of the nice one. That hey, the faster that fluid moves, the faster it moves, the lower the pressure, so it actually pulls it up higher in that location. Now, I'm pretty sure they call this a Venturi tube. I think that a Venturi tube is also like they use that kind of stuff in a carburetor. I don't know exactly how or where. I do know that there are some types of well pumps that use a thing kind of like that to draw extra water from the bottom. But we'll talk about that in some other time. So let's go through a calculation. No, boy. Oh, we're fine. Never mind. Okay. Let's go through a calculation that uses Bernoulli's principle, actually. So we're going to use this as our calculation. So we're going to take a look at number 3 on the bottom of the first, on the front of the page. I screwed up my numbering, so it says 3, but technically it's like the 4th numbered thing, but it says number 3. So I'm just going to remove my labels for this. I think, oh, actually, I got to talk about something else really quick. I think drawing pictures when we do these problems is helpful. Okay, so whenever I do these, I draw a picture, I label them. The things we're looking for with Bernoulli's are the things I've underlined in orange, green, and red. We really want to focus on pressures at location 1 and location 2. We want to look at heights at location 1 and location 2, and we want to look at velocities at location 1 and location 2. And if the area changes, we got to do a flow rate. We got to do an A1, V1 equals A2, V2 problem first. But I forgot this last part. There's a thing right here, and it says if a variable is the same right below, in between number 2 and number 2, the very last thing before the second number 2, it says if a variable is the same at both locations, you can/should cancel out the entire chunk with the term in it. So let's just mathematically talk about 3x plus 5 is equal to 7. It's a math problem. Okay, you don't have to write this down, I'm just trying to use this as a talking point. So we could solve this, we could combine like terms and all that good stuff. But what overall impact does, if we solve this for x, what is it, 2/3? It'd be 2/3, I believe. Correct? 2/3? Yeah, 2/3. I'm pretty sure it's 2/3. Minus 5, so that's going to be 2 divided by 3, 2/3. Okay, so my answer is 2/3. What happens to my overall answer for x if I add 500 to both sides? What impact does it have on x, my overall answer of x? Nothing, right? It doesn't change my overall answer. And you can say, are you sure? And the answer is pretty sure. Because if I were to not going to combine my blacks with my purples yet, I say, well, there's an x over here, let me move that 500 to the other side. So if I'm going to subtract 500 to this side, that goes away. Which then when I subtract 500 to this side, hey look, that side went away. It doesn't change my overall value of x. Now the reason I'm bringing that up is because of that thing that I wrote. If the variable is the same at both locations, you can and should cancel out the entire chunk that has that variable in it. So let's start with p. If my p had a value of say 500 at location 1, and my P2 had a value of say 500 at location 2, if I add 500 and I add 500, does that have an overall impact on my variable that I'm solving for? The answer is no. What if this is 100,000 and this is 100,000? No. What if this is a million and this is a million? The answer is no. So if my P1 and P2 are the same, I can cancel out the chunk that has, on both sides, that have the P's in it. But it has to be on both sides, they have to be the same, and then I can cancel out the things that have, the chunk that has the P's in it, which in this case it was just P1 and it was P2. Okay? But if I now have a velocity, and I have water flowing through a pipe with some velocity, and at location 2 I have water flowing through the pipe with some density and the same velocity, if I take 1/2 times 1,000 times 2 squared, and my density is the same at location 2, and my velocity is the same at location 2, so 1/2 times 1,000 times 2 squared, this is going to have the same as if I add 500 and 500. I can cancel the chunk from plus sign to plus sign that has the V in it at both locations, from plus sign to plus sign. I can cancel out the 1/2 rho V1 squared and 1/2 rho V2 squared. I can cancel out the chunks that have the same values in on both sides. If my heights are the same at location 1 and location 2, I can cancel the chunks that have the heights at location 1 and location 2. It's a way that kind of simplifies our problem a little bit. So, if we take a look at that number 3, it says a horizontal pipe, so that means the pipe is laying flat. A horizontal pipe with a radius of 0.08 meters has water flowing through it, V, of 4 meters per second. And a pressure, oh, there's a P, of 3 times 10 to the 5th. Now, if you hate scientific notation, move the decimal point 5 times to the right, and that's your answer. So 300,000. If the pipe, I'll write it, 300,000. If the pipe narrows to a radius of 0.04, the velocity is going to change. Stick my thumb over the end of the hose, velocity is going to go faster, right? So there's going to be a V. What is the new pressure in that pipe? This is comparing 2 different locations. This is talking about a radius at location 1. It's talking about a velocity at location 1. And it's talking about a pressure at location 1. There's a location 2, which has a R2, it has a V2, and it has a P2. The way we solve for P2 is we use Bernoulli's. We're going to solve this for P2 using Bernoulli's. But it says if the area changes, then the velocity is going to change, and we have to do a flow rate problem first. So before we can do a Bernoulli's calculation, we're going to have to do an A1 times V1 is equal to A2 times V2 calculation first, because that's the way I'm instructing you to do it. So V1, R1 can give us our A1, V2, R2 can give us our A2, we can then solve for this V2 value. So A1 is pi times R1 squared. A1 is equal to pi times 0.08 squared. A1, I'm going to get a number, and it's going to be a meter squared, and I'll do that in just a moment. We can do the same thing for A2. The only thing we change is we change what my R value is. Now I'm going to write down rounded values. I'm going to say it again. you want to try to keep every single digit you can, so I'm going to store those values in my calculator. Alright, so when I go through and I solve for A1, I get a value of 0.020. That's my A1. My A2 is 0.0050 meters squared. Now again, more digits stored in my calculator for later use. A1 is that, the A2 is that, which then we can now use my A1 times my V1, so 0.02 times 4 is equal to 0.005 times V2. And when we go through and we do this, and if I use all of the digits in my calculator that I have, and I don't round anything, we get 16. What happened is I cut my radius in half. A radius in half squared is I cut my area by a fourth, which means that my flow rate is constant, my velocity had to increase by a factor of 4. That's where that 16 comes from. But now I know my V2 is 16 meters per second. So now we're going to use Bernoulli's. Okay, now we're going to use Bernoulli's equation. So I'll start with it here and then I'll just kind of move. So if we look at Bernoulli's equation, it's really long, but if we have a variable that's the same at both locations, we can cancel out that chunk. So is my P1 and P2 the same at both locations? The answer would be, I don't know, we don't know what P2 is, you're right, we gotta keep it in there. Is my V1 the same as my V2? Is my V1 the same as V2? And the answer is yes, we cross off those chunks. The answer is no, then we gotta keep the chunk with the V's in it. And V1 is 4, V2 is 16, so no, we gotta keep the chunk with V2s. Is my H1 the same as my H2? And you can say you don't have a height label in your picture. You're right, I don't have a height label in my picture. But I have a horizontal pipe. So when we measure like the height of a pipe, we talk about the center of this pipe to the center of this pipe. And what's true about the center to the center? Well, it's the same. I'm not going uphill, I'm not going downhill, my H's aren't the same. So my H1 does equal H2. So what that says is if my H1 is equal to my H2, we can cancel out the chunk that has H1 and has H2 in it. So that's the chunk that has H1 in it. This is my chunk that has H2 in it. And I can cancel those values out because the density of my fluid is 1,000. Gravitational acceleration on Earth is 9.8 meters per second squared. And my H1 is any number you want. You could say H1 is 0 and H2 is 0, great. You could say H1 is 1 and H2 is 1, great, but you're adding the same number to both sides. You could say it's 1,000 and 1,000, great. You're adding the same number to both sides. They cancel out. That's what I mean by you can cancel out the chunk that has that variable in it. If my V were the same, I'd cancel out that chunk on both sides. If my P's were the same, I'd cancel the chunks on both sides. So I can cancel out things that are constant on both sides. If I have a value of 0, I can plug in that number and cancel an additional term out, but that's kind of where we start. So now I'm at the point where I can plug numbers in. So my P1 is 3 times 10 to the 5th, which is 300,000 Pascal if you don't like scientific notation. And that's going to be plus the density of water. Now if you don't know the density of water at this point is 1,000, that's okay. We've done it, we've used water so many times, I'm assuming you're starting to remember it. If not, it's probably listed. If not, ask. times the velocity of that water at location 1, which is 4, but don't forget to square it. It's 1/2 times the density of water times the velocity of that water at location 1 squared, which is equal to P2, that's what we're solving for, plus 1/2 times the density of water, 1,000, times the V2 that I calculated doing the flow rate problem, which is going to be 16 squared. So that's what we have before we combine like terms. 3 times 10 to the 5th, 300,000, plus 8,000 is equal to P2 plus 128,000. So 3 times 10 to the 5th, combine like terms, plus 8,000 minus 128,000. We get a P2 that's equal to 180,000 pascals. Now, Bernoulli's principle says that the faster a fluid moves, what happens to the pressure? Faster it moves, the lower or higher the pressure? Lower the pressure. So what happened to my velocity? It went from 4 to 16. Did I go faster or slower? Faster. So what should have happened to my pressure? Should have gone down. We started at 300,000 at P1, and it went down to 180,000. Now we can use Bernoulli's for a couple things. We can use Bernoulli's when we talk about changing velocities. We can use Bernoulli's when we talk about changing heights. So like we take a pipe and we pump water like up a hill. Or we can talk about that when we do both, or if we change the pressure, or different combinations. If our area changes, we have to do an A1 V1 equals A2 V2 first, because that gives us velocity, and then once we determine the velocity, then we can plug it into Bernoulli's. So Bernoulli's is really long, but it often cancels things out, because if things are constant at 2 locations, we can cancel out the chunk that has that term in. Okay? So tomorrow, I got more demos. I just ran out of time today. I had one more I was going to do for you today, but we'll get it tomorrow. So.